The area of a circle is pi times the square of its radius. It follows that the derivative of the area with respect to the radius is pi times the derivative with respect to the radius with respect to r of r squared, and the derivative with respect to r of r squared is just 2r. So we have 2 pi r for the derivative of a with respect to r. Now I'll note that the derivative of a with respect to r is a limiting value of change in a divided by change in r, which is a limiting value of the rate of change, the average rate of change of a with respect to r. This then is the instantaneous rate of change of a with respect to r. So this is the instantaneous rate of change of a with respect to r. Now, see a smudge, I need to fix that. Let's note immediately that if this is the instantaneous rate of change of a with respect to r, then, well, dA dr then is approximately equal to change in a divided by change in r. Change in a divided by change in r, of course, is average rate of change of a with respect to r. So that if we want to find the change in a, we can simply multiply the rate of change of a with respect to r by the change in r. We'll get an approximate value of the change in a. So from this, from the fact that the average rate of change of a with respect to r is close to the rate of change of a with respect to r, if you pick the right r for this expression, and we'll see that in a minute, then the change in a is approximately equal to this multiplied by delta r. So change in a, of course, equals delta a over delta r times delta r. Very obvious. If you multiply this out, you end up with delta a. But it's approximately equal to the instantaneous rate of change of a with respect to r multiplied by delta r under conditions that we'll discuss here shortly. Now, you're not asked to use this in the problem. The problem simply says, okay, find the derivative of a with respect to r, or the instantaneous rate of change of a with respect to r. We've done that. It's 2 pi r. Now, if we make a table, r values 1, 5, and 20, we're asked to find dA dr for each of these values of r. And that's very easily done. dA dr is 2 pi r. So we just multiply 2 pi by the value of r, and we get the value of dA dr. Multiplying 2 pi by r equals 1 gives us 2 pi. Multiplying by r equals 5 gives us 10 pi. And then plugging in r equals 20 into this expression, we get 40 pi. These are 3 values of the instantaneous rate of change of the area with respect to radius, corresponding to these 3 radii. Now, we have the question, okay, what is the approximate change in a if r changes from 10 to 10.5? Okay, well, first of all, we can find the actual change of a. If r is 10, then the area, well, we just plug in 10 into a equals pi r squared, we get 100 pi. And if r is 10.5, we plug that in, and we get 10.5 squared, which I believe is 110.25 times pi for the area. So the change in the area is 10.25 pi. However, if r is 10, which is the value we have here, what is dA dt? It's 20 pi. Now, if we multiply, no, it's not dA dt, it's dA dr. That r looked a lot like a t. And maybe I should edit that. Let me do that. Okay, change that to look more like an r. And that one looked like it could use a little help, so I changed it too. Okay, again, we find that the change in a from r equals 10 to 10.5 is 10.25 pi. However, using the dA dr value for r equals 10, which is 20 pi, if we multiply that, which represents, again, a rate of change, instantaneous rate of change of a with respect to r, if we multiply that by the change in r, which from 10 to 10.5 is 0.5, we get 10 pi. Okay, and I didn't really write that out completely, so let me stop and do that. Okay, just indicating that the dAdr is 20 pi, hopefully you can read that, and the delta R is 0.5, so I multiplied those to get to 10 pi. Now that's 10 pi, it's not 10.25 pi. Now we know that the change in the area between these two radii is 10.25 pi. So our estimate based on the instantaneous rate of change at R equals 10 is off by, well, turns out to be 2.5%. And the reason for that is that we just used the rate of change when R is equal to 10, whereas R is changing from 10 to 10.5. So the rate of change is also changing. We see how the rate of change, the dAdr, increases as R increases. Well, it's not going to increase much between R equals 10 and R equals 10.5, but it is going to increase a bit. And if we take account of all those increases, we find that the change really is 10.25 pi, which we calculated, of course, just by the brute force method, the simple method of calculating the area for the two values of R and subtracting. So what we did when we multiplied this one rate of change that applies only when R equals 10 by the change in R, which is a small change, we got something close to the actual change, but we did not get exactly the actual change. We underestimated it by 2.5%. And again, that's because the dAdr, that looks like a dt too, but I'm going to leave it. The dAdr changes, and it doesn't, leave an S on the end of that, it changes between R equals 10 and R equals 10.5. Again, it's kind of hard to write an R down here, but maybe I can improve it a little. Okay, so we used a static value of dAdr. We got a good approximation, but not an exact. And the actual is this, the predicted change is this, and the predicted change is an underestimate, since the actual value of dAdr is increasing. So the increasing dAdr would give you a greater change if you worked it out that way. Now, actually, before you were asked to do this, you were asked to fill in another line on the table, which would be the change in area if delta R equals 0.5 radius units at the calculated rate for each of these radii. So the calculated rate here is 2 pi. If we multiply 2 pi, and this calculated rate is in area units per radius unit. Okay, so this means as R changes, dAdr, well, has to be in area units divided by radius units, since dA is in area, a change in area, and a delta R is a change in radius. I should say a delta A is a change in area, a delta R is a change in radius, and a dAdr is a limiting value of a delta A over delta R, so that's also going to have units of whatever area units are divided by whatever radius units are. So that the rate at which the area changes as you change R when R equals 1 is 2 pi area units per radius unit. Here the change is 10 pi area units per radius unit. Here it's 40 pi area units per radius unit. Okay. So if delta R is 0.5 radius units and dAdr is 2 pi area units per radius unit from here, we get delta A is the rate times delta R, 2 pi area units per radius unit times 0.5 radius units. That's going to equal pi area units. At a rate of 10 pi area units per radius unit, multiplying that by the 0.5 radius units, we get the 5 pi area units. At a rate of 40 pi area units per radius unit, we get 20 pi area units for a radius change of 0.5 radius units. Applying that idea again down here, we get these results as we've discussed. And just to reinforce one of our main points, the change in area is the rate of change of area with respect to radius times the change in radius. That's what we're saying up here. Change in area is equal to the average rate of change of area with respect to radius, and I should put the word average in here, multiplied by the change in radius. The average rate of change of area with respect to radius will be close to the instantaneous rate of change if you pick the right radius from which to calculate your instantaneous rate of change. Okay, all this is very central to the things we want to think about when we, excuse me, are applying derivatives to various applications that involve rates. And there are many, many, many such applications in a wide variety of fields, which is why we have a calculus or an applied calculus course.